All right. So when you're talking about biology, you're talking about the cell. You're reading in chapter 7. Again, chapter 7, and that's the work there. I think this is the 5th time I've said it. I'm going to say it. I'll keep saying it just to remind you. One, you got to read chapter 7 and take notes. And it's just that simple. Read it and take notes. And what are you focusing on? The highlighted words, the key words, the main ideas. Where do you find the main ideas? The main ideas are in the study guide. At the end of the chapter, there's a study guide. Everybody has it. So you take notes. And you also have a practice test in the back of the chapter that you need to get done. So the study guide, you have questions, but you also have in the study guide, you have vocabulary for the chapter, and you have main ideas for each section. All right? So read and take notes, and I would start with going to the study guide, looking at the main ideas, what's important, and then start reading the section. There's 4 sections. There's a study guide. Well, it's one study guide, but yeah, they break it down by section. And you'll be able to identify, okay, what's going to be important about what I'm going to read. So it's called reading for understanding, and having a good idea of what's important before you even read is a good idea. So find the main ideas here. So when you're taking notes and you're doing Cornell notes and you're looking at main ideas and you're taking, I'm going to write about this main idea. Let's say it's about types of cells. I don't know. Whatever the main idea is for that section. Then over here you write down, prokaryote, eukaryote, and then you explain it, or you do a chart or whatever. But your main idea is here. That's the point. That it shows, what does that demonstrate? It demonstrates that you've reduced these really big concepts into something that's important, right? That's really what's key. That's really key to doing this thing called studying. That's what studying is. Anything else is not going to get you understanding. When you're feeling you're not ready for a test, when it feels you're confused about something, it's usually because you have not broken down the information in this way. Yeah. This is just an example, so you don't have to do this right now with this. Just an example of what you would do when you're reading, and you just focus on it. Don't copy the whole chapter. That's ridiculous. You have the chapter for reference anytime you want. What you want to do is you want to get the main ideas. You want to make sure you work those out. And once you've worked out an example or and maybe you have a question. Maybe you're like, I have to ask Mendoza, what kinds of life have no nucleus? Maybe you ask that question. Maybe you ask a question that like, for instance, do they have DNA? Maybe that's a question you can ask. What is that showing? This shows this, again, to emphasize, because some of you didn't get great grades on your binder. What does this mean? What this is showing is reflection. You're reflecting on what you understood, what you're confused about. And of course, that also means that you can ask these questions in class. And some of you say, well, I have your first period. It's hard for me to focus. I'm tired. I had a long night. Okay. Well, you have a video that's posted. You have work that's assigned. So you can do this when you are awake on your schedule. So there's options for you to get it done, but no matter what, you got to get it done. So what kinds of life? This is just an example. These are just examples, okay? So this is not necessarily something that you have to write down, but then over here you would have, whatever examples are in the chapter. And, maybe you put a little question mark on, hey, I don't understand this, or you highlight it and you think that's important. Maybe I should ask Mendoza if that's important. Let me ask in class. Maybe I say something that's opposite what the book says or is wrong. Sometimes I say things that are wrong. So, hey, Mr. Mendoza, the book says this. You're saying that. What's the deal? Those are great questions. Those are the kinds of things that a good student, someone who really is going to focus their minds and really get to that success, cross that finish line with it as a champion, that's what you got to do. And that's in every class. You got to do this every class. Someone else told me, well, I want to reflect and revise because I had a bunch of kids with decent stuff written down. They wrote the stuff that was done in class down, but they didn't go back and reflect. They didn't reduce. They didn't summarize, right? They didn't highlight. They didn't do the 6 R's. So now, you don't have to do any one of those things, but you have to do at least one of each of those 6 categories. You don't have to do them all. Could you close the door, please? So the question is, how are you going to be like? And they say, well, I had to spend my time studying for the world history test. I had to spend my time studying for doing Mr. Pennypacker's work. I say, okay, but I have to reflect and think about how I can have you make sure that you understand this is a serious thing. And if I have to every day collect yesterday's notes to see, and I would collect it on Thursday during this Fast 7, we're going to go over how to scan your notes and turn them in online because I want to make sure I do that before I require it. But you'll scan them, you'll upload them online. So I could have you upload every day's notes online. That could be your daily homework, right? If that helps you, make sure to remind you that, yeah, I got to do this. Like, I don't want to give you, I'm trying not to give you all this homework. I'm trying to tell you, look, all you got to do is go back, reflect, go over these notes, do this stuff. But I understand that you get distracted with other things like math homework and world history homework. So maybe you need, and that's something for you to reflect on, maybe you need something due. Maybe that helps you if you look at Schoology, you say, wow, I got to get these notes turned in because they're 50 points every day. I got to take the notes, I got to reflect, I got to reduce. If that's what you guys need, then that's what I get done. But I don't want to see notebooks where you guys are just writing stuff down and you're not using it after you walk out of the class. I think that that's not really useful. I think that's a waste of your time. It's a waste of resources, a waste of your time. And I feel like you're not learning as much as you could learn from what we're doing in class. That goes for, the mini lab report. The mini lab report should have been easy. Just a single page, a few paragraphs explaining what you observed. Asking some questions, answering some questions. That's it. Not a big deal. Yet a lot of people didn't do it, and I wonder why. And I just got to think you forgot about it. Because you did the lab, but you just forgot about it because you had so many other things to do. So if you need me to put it in Schoology as something that's due daily, I can do that, okay, if that helps you. All right, let's move on then. So that being said, today let's talk about this thing we started with, phospholipids. Phospholipids, again, is a phosphate group. There's several other things on it. And they have the 3 carbon glycerol, and to one of these carbons, let me draw it. You don't have to. You can draw it if you want to remember what it is about. I hate to draw things and you're just like, whatever, it's a phospholipid, blah, 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 he says. But I don't want you to think.
Are those seeds?
Yeah, those are C's, carbons. And there's hydrogens on all these. If there's single bonded hydrogens on all these, what is this? Let's think again. If they're everything's full, saturated, that's right. So this is saturated fatty acid. The acid part is a carboxyl group that's attached. It's not a carboxyl group anymore, but it was at the end here. And this is attached now through dehydration synthesis. We attached it to a glycerol molecule. So there you have it. That's one fatty acid. And then to the last of the carbons, there's another fatty acid attached. And let me give myself a little more space to draw this. I'm trying to draw it big enough for you guys to see it. And you have these drawn already in your biomolecule questions. Your biomolecule questions, you have these already drawn by, professionally. But sometimes a carbon has a double bond. And that makes it unsaturated, is correct. And there's, of course, hydrogens on each of the single bonds at the end of each of the single bonds, a hydrogen or a carbon. That's why we call it a hydrocarbon. So this has a kink to it. You see how it kinks out? Yeah. Okay, that's going to become important as we talk about cell membranes. This is called a phospholipid. I keep running out of room, I'm sorry. Phospholipid, all right? Phospho because you have a phosphorus on it. Phospho because you have phosphorus on it. And lipid because it's a lipid. You have fatty acids. The fatty acids here make it a lipid. The big phosphate group. It's a bigger group. It's not just phosphorus. But there's phosphorus in there. Now, every cell in your body has these things. So let's talk about what they are. We got a phosphate head. And usually they're drawn this way. This is drawn this way, usually. They just draw a wiggly line and then one that kinks out. So they'll usually draw something like that. This represents a long carbon chain, and the other one represents a long carbon chain that's unsaturated. One is saturated, it's straight. The other is unsaturated, it kinks out. Kicks out. Now again, that becomes very important. Yeah? So phospholipid is a very interesting molecule. We talked about these idea of polar bonds before. So we talked about sharing, and we said, look, if oxygen and hydrogen, we looked at water, and we said water has this partial negative charge, hydrogen has this partial positive charge. And so when you have water hanging out together, what happens is that water forms these attractions. There's these attractions, not inside the molecule, but between molecules. Do you understand the difference between molecules and inside the molecule? Yes or no?
No.
What's a molecule here? I'm drawing all the... Where do you see a molecule? Where do you see a molecule here, guys? All molecules is correct. But what are they? What are the molecules here? H2O, water. This is a water molecule. It's a single water molecule. Is that correct? Do you understand that? So what holds the molecule together is called covalent bonds. Covalent bonds. But there are forces that hold water together. Why does water stick together? Why is water sticky? Is water sticky?
No.
Yes, it is. It's very sticky.
Gravity.
You get out of the shower. You get out of the shower. Does the water just fall off you? Does gravity pull that water off?
Yeah.
Really?
Yeah.
As soon as you walk out of the shower, you're dry because all the water fell off. No, well, you got to work at drying. You got to work. You dry your hair, you got to use a towel, maybe a blow dryer. You got to use towels on the floor. Yes, some water falls off. Gravity does pull it off. But you got to dry you have to spend a lot of time drying. Water holds together well. It's very sticky. What'd you say? Okay, it's not funny. So water sticks to itself. What does that mean, sticking? It sticks to itself because it has these attractive forces between the molecules. They're weaker than covalent bonds, much weaker than covalent bonds, but they make a big deal. They're a big difference. Right. Covalent bonds are what holds the atoms together. The covalent bond is the sharing of electrons between atoms. And when it's done unevenly, you have one atom being partially negative, that's that delta sign, another atom being partially positive, and they line up like this and they attract each other. Now, if you've ever seen water droplets, if you ever seen a drop of water on a table, we used to do an experiment. We don't have time to do it now, but you could take a penny. You could do this at home if you like. You could do this with anything. That's a horrible penny, but whatever. And you could drop water, and what'll happen? It'll look like a bubble, but it's not a bubble. It's actually just it's a bunch of water, millions, billions of water molecules all sticking to each other. And when you look at the water droplet, it's clear. Obviously, it's clear. It's clear. But when you look at the water droplet here, it doesn't fall off. Gravity doesn't pull it off. It goes up. Like, how do these water molecules stack up on top of each other? There's gravity pulling them down. What's holding it together? That force, that green force that we're going to name in a minute. We haven't named it yet. Well, we have, but you don't remember it. That force is holding these water molecules together. If you looked inside, what you would see is this. You'd see a bunch of water molecules all sticking to each other through this force. It's an invisible force like the force of that you see in magnets. You don't see the force in magnets, but magnets stick together, right? So this is a positive and a negative, so they're going to stick together just like magnets, and they hold each other into this bubble. So water will form a drop. That's why water just doesn't fall into molecules, it falls in drops. And when you pour water, it pours as a unit, doesn't it? You don't just get one drop of water leaving if you start pouring. All the water flows, right? Why does it flow? Because the force, as one molecule starts falling, come here, arms. Both of you. Well, as one molecule starts falling, it takes the others with them. And then they take the others behind them, and they all flow together. The force pulls everything together. That force is strong enough to allow, on a pond, to allow a spider to walk on water.
I can?
Right? You've seen water striders?
No.
You've seen well, look it up when you get a chance. Not now. Look it up when you get a chance. You'll see spiders walk on water. How do they walk on water?
Because they stick.
Stop. They're wet.
No.
Because of the fractive.
Their legs are so
What is it allows a spider to walk on water is that the water molecules that it's stepping on, it's stepping, but the water molecules are sticking together. It's hard for the spider is light enough and it spreads its feet wide enough that the force that holds the water molecule together doesn't break. And so the spider can walk on it. You and me, we step on the water, we fall through because we're too heavy, and all the force of gravity is strong enough that it breaks the connection between the water molecules. We call that surface tension. That is called surface tension. So that's the ability of water to stick to itself. So that causes surface tension, and we call that cohesion.
I heard that word before.
Cohesion is the ability of something to stick to itself. To stick to itself. So cohesion is when something sticks to itself. So the surface tension of water is due to cohesion. Now, and of course, cohesion is due to this force between molecules. So it's due to the force between molecules, this idea of cohesion, the idea that water. The other interesting part, if you took this idea of liquid, gas, and solid, you've heard of this, right? Solid, liquid, and gas. Have you ever heard of solid, liquid, and gas?
No.
It's matter.
Oh.
So you have a glass of water. And you have a glass of alcohol.
Oh, like what?
A glass of pure rubbing alcohol. Rubbing alcohol. You're not going to drink it. Never drink rubbing alcohol. It will make you blind. You could die, but certainly you'll go blind. All right. Don't drink it. I don't know what you're saying, but I'm going to ignore you for right now. So these are all made of molecules. I'm just drawing dots. We know what water looks like. Ethanol is, I'm not going to draw it for you because it's just added information you don't know. It's also made of molecules. They're small. They're about the same size, ethanol. In fact, if it was methanol, it would be about the same size. But what's interesting is that the boiling point, what does it mean for something to turn into gas? Let's call it the vapor point. The heat of evaporation, or the boiling point of water. The boiling point of water is 100 degrees Celsius. So at 100 degrees Celsius, these molecules, they start to go. And what it is this idea of kinetic energy. Right? Kinetic energy is the energy of molecules. Everything's moving. So these molecules are all vibrating in 2 directions and 3 directions and 4 directions and 5. It's moving in every direction. They're vibrating, moving back and forth. And this one's zipping over here, bounces off that one, and zips over there, and this one zips over here. They're constantly moving. They have kinetic energy, these molecules. So do these. These also are moving, and they have a kinetic energy. The average kinetic energy is measured by temperature. So temperature is telling you how much are these molecules moving. So you're looking at water at 100 degrees Celsius. It's moving at a certain speed. It's sort of like going 100 miles an hour. So you would expect when at 100 degrees, then what happens is at 100 degrees, they're moving so fast that the molecules zoop right, they just leave. That they turn to vapor is correct. They turn into vapor. The molecules of gas water are still H2O. They're still being held together because those are very strong bonds, those covalent bonds. But these molecules are now going off into empty space. They leave the liquid. But what's interesting to me is the boiling point of something a substance that's very similar, of an alcohol like ethanol or methanol. The boiling point is around 70 degrees. So at only 70 degrees Celsius, these little molecules, they take off. They turn into gas. Now why? Why does it take less kinetic energy for these molecules to leave the liquid form?
It is less sticky.
They're less sticky. Excellent. You're listening, you're thinking. Good. They're less sticky. Excellent. So what it is that these water molecules are all sticking together. They have a lot of cohesion because they have a strong force between them. But these alcohol molecules are what we call non-polar. These water molecules are what we call polar. So polar molecules tend to have a lot more cohesion. They stick together more, so it's harder to get them to turn into gas. They have a higher boiling point. Non-polar materials, they have a lower boiling point. They can turn into gas faster. Now, the bigger the molecule, the harder it is for it to turn to gas. I'm talking about the vapor, turning into vapor. Now, gasoline is a liquid at room temperature, but what happens when you take the cap off the gas can? What happens right away? It turns to gas. It turns into vapor right away. Even though gasoline is a very big molecule, because it's very nonpolar. It's very nonpolar. It does still evaporates very quickly. If you leave gas alone, it'll turn into a vapor very quickly. If you leave gasoline alone. So nonpolar molecules evaporate at lower temperatures than polar molecules. So when the boiling point of something is due to two things. It's their size, how big the molecule is, and how sticky it is, how polar it is. Yeah.
What would happen if you combine both of those together?
You're amazing. That's exactly where I'm going. That's the next step. So does everybody get that? So we call this thing, this stuff nonpolar, this stuff polar. There's something else that's interesting about polar and nonpolar molecules. There's a rule of thumb. It's called the rule of thumb because it works most of the time. So let's be clear what it is. Like dissolves like. So what it is that polar materials, polar and ionic materials, huh?
It's two S's.
What? Oh, so all right. So like dissolves like. It's polar and our ionic materials dissolve with two S's. Polar / ionic materials. All right? That's it. Now, what do I mean by ionic? I mean things like salt and sugar. Salt is ionic. They're not molecules. When you look at salt, you're looking at Na plus has a full positive charge and a chlorine negative. There's no sharing. They don't share electrons. Chlorine took it, sodium gave it. They just stick together because they're charged. We call those ionic substances. Often we call them salts. All right? So salt dissolves in water because water's polar and salt's ionic, like dissolves like. Is that clear? That's why. But when you look at nonpolar materials, so nonpolar materials, dissolve nonpolar materials. I'm going to give you a couple. So if I took and I put in that water, I put oil, what would happen to the oil?
It'll go up to the surface and
It'll be on the surface. It would not mix. It will not dissolve. Why?
Because
They're not like. Oil is
a non
nonpolar and water is polar. They don't mix. That's why oil doesn't mix with water, because oil will not easily. They'll mix, but it's difficult.
oil is less sticky, that's why.
No, oil is.
Oil is less sticky and water is very sticky. So the
So it
two,
rises to the top.
so that they don't like each other. They don't mix.
So it rises to the top.
So it's at the top. The reason it's at the top and not, if you have a dense oil, it would be at the bottom. You can make. There are some oils. I'm assuming you can make an oil that would sit at the bottom. They would layer at the bottom, and yes, you can have that. Like mineral oil will sit at the bottom of water, but they just don't mix. They don't dissolve each other. Dissolving means mixing really well. Okay, so either they're going to dissolve or they're not. Now, if I put salt in there, what would happen? It dissolves. Now, here's another example. Nail polish. Girls in this room, y'all, if you don't wear nail polish, you've at least seen them. Some of the boys have nail polish. So, nail polish. Why doesn't it wash off when you put it in water?
Because
It's non-polar.
yeah.
So, what do you do to get it off?
Acid.
Acetone. So, what is acetone? Non-polar. So, non-polar dissolves non-polar. That's why you have to use something like acetone. Permanent markers. Permanent markers. Expo markers are not permanent. Permanent markers. It's non-polar. That's why they call them permanent, because it won't wash off easily. But all you gotta do is take some acetone. It'll wipe right off. Why? Because it's non-polar. Like dissolves like. Well, I think that's a good beginning. Tomorrow is
So like rubbing
Thursday already. Dang.
No, like rubbing alcohol, any rubbing white